Okay, we are recording. Mm-hmm. 21, 22. Ooh. Okay, can everybody see my screen, I hope?
Yes.
Excellent. All right then, let's get on with things. Last time we ended up in chapter 2 talking about vectors in general and how vectors behave kind of pictorially. Now we're going to get into how we're going to represent vectors mathematically. It's going to make the manipulation of vectors much simpler and much more precise than it is just trying to draw things that, you know, draw arrows, perfect length and at perfect angles. So we start by choosing a coordinate system, of course. We're going to choose an X and Y coordinate system here. Man, I wish I had a bigger screen, but I just don't. Anyway, we have our X coordinate. We're going to choose going to the right in the horizontal direction. Our vertical direction will be our Y, positive direction. Of course, they're 90 degrees and orthogonal, which is great. And we're going to create a unit vector in each direction. For the X direction, we're going to create the unit vector I hat. If you remember last time, we had a unit vector called U hat. We're going to call this one I hat. And we're going to call the one that goes in the Y direction J hat. And this is the thing that sometimes changes. Sometimes you'll hear physicists and engineers call these X hat and Y hat, and that's totally fine. I actually prefer that. I think it just makes sense. But we're going ahead with what the book is doing here, and it's good to use different things anyway so that you get used to people changing things up on you, because it does happen. But I'd say probably a good 90% of the world in physics and engineering uses I hat and J hat for X and Y unit vectors respectively. If you are trying to represent a vector in this coordinate system, you can do so by using the addition of vectors. So here is our vector A pointing upward to the right here. They don't really show it by itself anywhere here. But our vector A is this vector that starts at the point B and goes up here to the point E, pointing upward and to the right. And it is actually the sum of two vectors, one that points only in the X direction, which we call A sub X, and the other one which points only in the Y direction, which we call A sub Y. And these are what we define as the components of this vector in this coordinate system. Components of a vector are always vectors that you can add together to make the vector of interest, but those components are usually vectors that only point completely in the direction of one of your cardinal directions or one of your axes, right? So you have A, we call this A sub X, or the X component of A. We call this A sub Y, or the Y component of A. They are vectors by themselves. And when you add them together, they become the vector A. They actually result in the vector A. The vector A sub X is often called a projection, or the components of a vector in a particular coordinate system are often called projections of the vector. And the reason they're called projections is because if you can imagine a light being shown downward upon this vector from straight above it onto the x-axis, the the vector A would leave this shadow on the x-axis that is the length of A sub x. All right, that's the shadow, so it's called the projection. You do the same thing from the right towards the y-axis, and you would get a projection of the vector onto the y-axis, which is the same length as vector A sub y. And both of these vectors, A sub x and A sub y, have a magnitude and a direction. The magnitude would be the length of the vector, essentially, right? And we usually denote that using A sub x without any boldface or arrow over the top. Later in this book, we will stop using the arrows over the top just to save time and ink, I guess. But we'll just have all vectors will be just boldface. But anything that's a magnitude of a vector will not be boldface. It will be just regular case. And if it's the magnitude of a component of a vector, there will always be the subscript with one of the coordinates in it. So in this case, the subscript x, showing that this is the x component of this vector. And then the direction is shown by tacking the unit vector on it. Because if you multiply any number by a unit vector, it doesn't change the number at all, except that it gives it direction. The unit vector is equal to 1 times a direction. In this case, it's 1 times the x direction, which is I hat. So our component of A sub x is equal to A sub x magnitude times I hat, and our component A sub y vector is equal to A sub y magnitude times j hat, right? So that's simple. And if you write that out into a summation form or to a completed form, you get something like this. It looks kind of like a polynomial where you have two variables, you know, I hat and j hat, and you have two they don't call them magnitudes and polynomials. What do they call them? Call them coefficients, right? Where you have two coefficients, A sub x and A sub y. So it looks kind of like this weird looking polynomial, and it also behaves much like a polynomial when you're adding them, for example. When you add vectors together, then you are only going to add like terms, right? So anything that's I hat can be added to anything else that's I hat or subtracted anything else. And the same with the j hat. When you're multiplying, however, it also behaves like a polynomial somewhat. Not exactly, but kind of. And we'll see how that goes here later. Another thing that is good to know is that you can actually calculate the magnitude of these points, or not these points, these vectors, these components, as they're called. I always want to call them coefficients, but they're components. So you can actually calculate the magnitude of these components if you know the beginning point and end point of the vector that they come from. So if your vector starts at point B, for example, in this case, it starts at x sub b and y sub b, and it ends at point E, or does it the other way around? I can't remember. I think it's actually the other way around. Let's see. Nope, starts at B and ends at E. So if it starts at B and ends at E, then you take your end point x coordinate and you subtract off your B point or your beginning point. So this is beginning and end, I guess, right? So end point x minus beginning point x, and then your end point y coordinate minus your beginning point y coordinate to find the magnitude of the A component of the vector. So that's a useful thing if you know the end points of your vector and the beginning points of your vector. This is actually something that has a great deal of application in our everyday world, especially now that everybody's got a computer in their pocket. This is exactly how finger pointing works on your. This is a big has a lot to do with how finger gestures on your phone work. And believe it or not, that was not easy to make that work out. This is the reason that we didn't have touch screens and touch phones 50 years ago. We knew basically how to do it, but working it out was difficult. The engineering side was very difficult. And they started making touch screens that worked terribly more than 50 years ago. In fact, if you were a kid in my day, you could actually walk up to your TV screen and touch it, and you could actually see the beam change because the screen was made by beams of electrons hitting a phosphorescent screen. And so you could actually touch the screen and it would actually change how the beam behaved because your finger changed the charge on the screen, which changed how the electrons behave there. And if you brought a magnet near the screen, you could really screw it up because magnets really affect the path of electrons. And if you did that, you often had to de-gauss your television. There's usually a button on the television that would remove residual charges from the screen and restore everything back to normal. But your parents would get all mad at you because that button was usually on the back and you had to unscrew some panel to get to it. It was a big mess. And sometimes it just ruined the screen permanently, but it was super fun. Did you have a question? Yeah, so CRT, which stands for cathode ray tube, right? A cathode, the cathode is the positively charged end of an electrical potential difference kind of thing. So if you have a voltage between 2 points, the cathode is the positive side, or the higher voltage side, I guess you could say. And the ray that was part of that cathode ray was the ray or the beam of electrons. And then the tube, of course, this was all taking place in a vacuum tube. So that's why it was called cathode ray tube or CRT screens. Yeah. And there was more than one thing that was fun about those televisions. When I was in college, we were given the assignment to design an electrical device of some kind, and we had to come up with a potential project, and then we had to present it to our professor. And the first one we came up with, we wanted to design a Z-pinch. If you've never heard of a Z-pinch, a Z-pinch is it's an electromagnetic device that creates a huge burst of concentrated electromagnetic energy. And it has the effect of essentially destroying electronics. That's what it does. And it's actually a weapon. And we actually wanted to use it as such. We wanted to use it to destroy electronics in people's cars who we didn't like their music. We thought we'd just go downtown and zap somebody's car when they were playing music we didn't like. Our professor shot that one down, no pun intended, but he wouldn't let us build the Z-pinch. But if we were going to build the Z-pinch, we probably would have still needed the same equipment. The second thing we came up with was an ion engine. So we wanted to design a UFO, essentially, an engine that will work in space or on Earth, and will allow you to levitate things using just electricity. It requires no movement of gases, requires no moving parts. It's essentially just using electricity. The electricity draws particles through the engine, and that creates a change in momentum, which pushes the engine upward or pushes it in the opposite direction that the particles are moving through it. And it works in space too, because there are still particles in space. There just aren't as many. In fact, NASA does use ion engines on their satellites to move their satellites around. The great thing about ion engines, they take very little energy, even though they use electricity a little bit, it's not much. And they're extremely efficient. And so anyway, we decided we'd design this thing. And unfortunately, we calculated that we would need like 15,000 volts of potential. We'd need a really high voltage thing. And the only thing that we had access to that had that much voltage was old computer screens, old TV screens. So we took apart an old computer screen and hooked our thing up to it. And it was kind of dangerous. I don't ever recommend doing this. We could have hurt ourselves pretty badly, but we did it anyway. And we actually made an ion engine. We actually got this thing to float. It was made of wire and balsa wood and aluminum foil. So it actually looked like a UFO as well. But we actually got it to float up off the table, and we tied some strings to it so it wouldn't float up to the ceiling, because it actually did that when we tested it. So we decided to tie some strings to it so it would stop. Well, it turns out that we got a little leakage current, which means the current was leaking from the top of the engine down to the bottom of the engine, which it's not supposed to do, and it was leaking through the wood. So we had current moving through the balsa wood, and that actually heated up the balsa wood, and then it caught on fire. So our UFO flew, but then it caught on fire in class. It was pretty awesome. So anyway, I don't know how I got off on that, but I did. Anyway, TV screens, that's how I got off on that. So TV screens use this idea of knowing where things are in a grid, in a coordinate system, right? And using that to map things out. Not only does it know where your finger is pushing, but it knows what is on the screen at that position as well. Because when you write a program, if you're going to write a program that is an interface, like that has buttons on it and things like this, you have to choose exactly where that button is. You have to choose where you're going to draw it. And then you also have to choose an area of influence for the button. In other words, when the screen detects a finger near it, which it does by using the electric fields in the things that actually make the screen glow, because there's little microchips in the screen that make the screen glow. You could think of it as that, I suppose. But anyway, as those things glow, if a finger comes near them, your finger affects how they glow. It affects the electricity going to them. And so the computer detects that change, and then it says, wait, is there a button at that point? And if there is a button at that point in the program, then it activates whatever that button is connected to, and then it does something in the program. Right? So it's very much a part of our everyday lives, this whole idea of coordinate systems and vectors and everything else. And of course, you're very used to sliding your fingers across the screen. And that, again, is very much about this math. They actually have to do this math of figuring out what is the magnitude of a vector, because the bigger you swipe across the screen, the faster the screen moves. The direction that you swipe across the screen matters. How many fingers you're swiping with matters, right? So all these things are, this math is actually programmed in your phone. This kind of math, much more complex than this, in fact, for all the different things you can do. And it was not easy to do that, to make it work right. Anyway, so they're actually going to use this example for the displacement of a mouse pointer. They're going from an initial position to a final position. We're going to calculate all that we can calculate about that vector that goes from that initial position to that final position. Well, to calculate the x component of that vector, we take the end point in x and subtract the initial point in x, and we get to the magnitude of that vector. It also gives us a direction. It gives us a negative 4.0 centimeters. So we know magnitude and direction from that calculation. Do the same thing in y. We get a magnitude and direction for the y. And now we know the magnitudes of the components of our vector. To build the vector, all we need to do is match up those magnitudes, which they're with their unit vectors, and that's what they do right here. So the d vector, or the displacement vector of that movement across the screen, is d sub x I hat plus d sub y j hat, which happens to be negative 4 centimeters I hat plus 2.9 centimeters j hat, which can also be written as negative 4.0 I hat plus 2.9 j hat, and then put the centimeters on the outside of parentheses. So it looks like this. Here's your x component, here's your y component. We know that our x component was negative, so obviously it's going to be pointing in the left direction, which is our negative direction. And the y component was positive, points in the positive direction, so the overall vector is pointing upward into the left, and that is the result. Now, neither of these magnitudes, dx or dy, the negative 4 or the 2.9, neither of those is the magnitude of this vector. Neither of them tells us the actual length of this vector. It tells us the length of the components of the vector. In order to get the length of the actual vector, we're going to have to use some other knowledge that we have, right? So we know that these three vectors will create a triangle if we set them up correctly. So if we take this vector, this component of the vector dy, and slide it over here and put it right here, then this becomes a right triangle, right? And then you can calculate the hypotenuse of that right triangle, which happens to be the magnitude of our overall vector, by using the Pythagorean theorem. You can take dx squared plus dy squared, the magnitudes, square the magnitudes, add them together, take the square root, and then you can get the magnitude of d. In this case, it'd be 4 squared plus, what was the other one? .9, right? So 4 squared plus roughly 3 squared. So it's going to be about 25, a little bit less than 25. So our magnitude over a vector will be slightly less than the square root of 25, or slightly less than 5. And here they show the Pythagorean theorem, in case you've forgotten that It turns out that there's also a Pythagorean theorem in 3 dimensions. If you have an x, a y, and a z, then it's a sub x squared plus a sub y squared plus a sub z squared, right?
Sorry, it just keeps going off of that. 'Cause I looked it up.
Yes, it
It
does.
just keeps going. But
Yes, the Pythagorean theorem can be used in many, many dimensions. And you think, well, why would you need more than 3 dimensions? Well, there is a strong evidence that there are more than 3 dimensions. How strong? Don't ask me. I'm not a cosmologist, not a theoretician. But there are people out there that do study that. Einstein was one of the first to really get into that. And he actually developed a new way of doing math so that you can do that. And if you're interested in that, you need to take modern physics. Yes, sir.
how do we know, and I guess if you're interested in that, take modern physics, this might not be a question to ask, but how do we know the Pythagorean theorem extends beyond the 3rd dimension? Which I guess we might not technically know, but for sure the 3rd dimension. How do we? I mean, it works.
So that's a good question. There are mathematicians and scientists who do theoretical work to try to prove that theoretically. Of course, proving it practically speaking it's not within our realm of possibilities at the moment. We haven't figured out how to deal with the possibility of multiple or more dimensions. Eventually we may not, who knows? But that's the way science goes. That's the way true science is. True science is you take these observations that you make and you build models from them, and you test your models until you come up with a theory of why that model works, or a theory of how the universe is working around you. And then you develop a theory and you start testing your theories. And the theories, so the difference between a model and a theory is a model is kind of like an analogy, whereas a theory is more like an explanation, right? And usually your models usually have mathematics that are not necessarily based on anything logical. They're just based on this is what we think it works like, right? Electricity kind of works like flowing water, right? But then once you get to a theory, you're using things that you've learned by testing your model to create a mathematical explanation of what's going on. This is what we think is really happening at a fundamental level. And then you start testing that theory, but because the mathematics in your theory are based more on fundamental understanding, laws of the universe, and things like that, logic things, you can use those theories to look for the next thing that might happen. So you say, well, what if this happened? What would happen according to this theory? So you start running the numbers through your theoretical projections, and you get some kind of possibility, some kind of outcome, right? And then you start looking for that outcome in nature. You start seeing if your theory is correct. So if you find that outcome in nature, then you go and look at what caused that outcome, and you kind of work backwards and you say, oh, look, in nature, it worked kind of like we thought. Or look, we found this outcome in nature, but it's not caused by what we thought it would be caused by. Or look, we can't find this outcome in nature at all. So maybe our theory is wrong or whatever. So it's, so these kinds of things, we're always pushing the theory beyond what we can actually test. And then we try to test it. And usually that testing comes later when we gain the ability to do it, or figure out how to do it, or we understand something, or we actually observe things that actually happen. So, an example of this is that Einstein predicted that energy, using theory, pure mathematics, he showed that energy and mass, could be interchangeable, that E equals mc squared. But there was no way to prove that. We had no experiment for it until somebody came along like 30 years later and said, oh, you know what? We bombarded uranium with neutrons. And instead of the uranium just absorbing neutrons like most things do, and maybe turning into a new element, it actually broke uranium into 2 other elements, 2 smaller elements, and then it released a ton of energy. But that energy was not there before. We actually created more energy out than we put in, a lot more. And so how do you get more energy out than you put in? Because that's never happened before. Well, it turns out that E equals mc squared explained it and matched up with the amount of energy we got. So they were able to show that, hey, we've got this phenomenon that Einstein predicted. And then they backed through it and they said, well, what do we think caused it? Well, maybe there was some mass loss that turned into pure energy, and they were able to measure that. And it turns out that it matched what Einstein predicted, right? And so people are doing that all the time, including with this, but we just haven't figured out a way to actually do an experiment to prove that it's correct yet. Eventually, maybe not. Maybe someday we'll figure out what another dimension looks like, how we would possibly detect it, how we would do experiments in it. Are we close? Maybe. I think so. I think we're close. We've recently discovered that the universe, both space and time, bend and flex and stretch, right? We'd actually already seen it bend and flex, but we hadn't seen it expand really. And we recently have actually measured that. So that's kind of interesting. We've seen it expand and contract, which means both time and space are not constant. They move, they change, which means everything around us, including us, we change with it, right? It's not constant. So quite interesting. Good question, but the short answer is, I don't know. Take modern physics and then you'll know as much as I know. Well, if you have to take modern physics and then another quantum mechanics class and another electrodynamics class. It's good 8 years more of education, and you'll know as much as I know, but you still won't know enough to really answer that question. Then you could take 4 more years of theoretical physics and know more than I'll ever know, and still not know the real answer. Yeah. If you do ever find the answer, though, tell me. We'll share the Nobel Prize. Okay. Any other questions? We good? Okay, Pythagorean theorem. Also from trigonometry, we also can calculate the angle if we know 2 of the sides, right? So we know the 2 sides, the 2 components, so we can calculate the angle using the tangent. It's the opposite over the adjacent, right? So AY over AX gives you the angle that is opposite your Y component, right? So that gives you one of the angles. Once you found one of the angles of that triangle, you can find them all because you already know one of them is 90. So you're good to go, right? And here's that triangle again. Remember that your angle has, you need to measure your angle from the same place as everybody else is measuring their angles. Otherwise, communication can get a little bit messy. In physics, we generally measure our angle from the positive x-axis and go counterclockwise. And that comes from something that we call a right-handed system in physics and math. In physics and math, we generally always use a right-handed coordinate system unless you specifically state that you're not using a right-handed coordinate system. And we also generally use a right-handed Cartesian coordinate system, which means it's always 90 degrees between the coordinates or between the axes. So for your standard rectangular coordinate system, a right-handed system means that you take your right hand. Everybody do this with me because we're going to be doing this a lot in this class. The right-hand rule is pretty important. Raise your right hand with me. Come on, we're going to take an oath of mathematics, right? So you raise your right hand. You're going to like karate chop your hand in the direction of your first coordinate, X. So my X is going to be to my left, to my right as I'm facing it. So I'm going to karate chop in the direction of my X, right? And then I'm going to rotate my hand until I can turn my hand in the direction of my Y. Turn my fingers in the direction of my Y. And then I turn my fingers in the direction of my Y. That's my Y. So X, Y. Y is up. And then your thumb will automatically be pointing if you did your karate chop, correct? Your thumb will automatically be pointing in the direction of your third coordinate, Z, right? So that tells you which direction Z should be going. So if we have a coordinate system if we're looking at the one on the screen here, the one on the screen has X pointing, as I'm looking at it, to my right. And then my Y is pointing up, so my Z would be coming out of the page, okay? So your Z coordinate is coming out of the page in this case. Can you have it go into the page? Yeah, if your X was going to the left, you could have it going into the page, right? Because then that would be X, and then you'd rotate your hand Z, Y, and then Z would go into the page. It's a little bit weird, but you'll get used to it. We'll do quite a bit of this in this class using the right hand to determine directions of things. Directions are arbitrary. It's a thing you choose, but you don't want it to be random, because you want people in Mexico to understand the physics we're doing in the United States. And you want people in Senegal to understand the physics that they're doing over in Pakistan or whatever else, right? So you don't want to, everybody wants to be doing same things the same way. And this is why we use counterclockwise for the direction that we measure our angle from the x-axis, because that's the right hand rule. We're going to karate chop into the x, turn our hand into the y, and then our angle is measured in that direction with our right hand, the way our right hand is rolling, think of it as. So that's the reason so angles are measured from the x-axis towards the y-axis in the counterclockwise direction, and that's considered a positive angle that direction. If you go the other way, it's considered a negative angle. So if you start at the x-axis and go downward towards the negative y-axis, that's considered negative angle. Okay. If you measure from the negative x-axis and go somewhere, then you're going to confuse people. Okay. We measure from the positive x-axis around. Now, you always measure from the positive x-axis around when you're trying to communicate. When you're doing your math for yourself and your homework, you don't necessarily have to do that, because sometimes that's inconvenient. Like when you have a vector that's all the way over here in the second quadrant, right? You don't want to measure this angle. You want to measure this angle. You want your angles to add up to be 180 inside your triangle, and your triangle's over here now, right? So you want it to be nice. So you do that for your math, and that's totally fine. But you do have to remember that your math may not work out perfectly the way you want it to. For example, if you do some trigonometry over here and you're using this angle, it's going, and you use, let's say that you use the cosine to calculate the length of this side, it's going to tell you the length of this side is a positive number, but this vector has a coordinate, has a component that's actually negative. So you just have to keep track of which way your things are pointing, and we do that by drawing pictures. So draw pictures whenever you're dealing with vectors. If you don't, I guarantee you'll screw something up. It's just a fact. So make sure you're drawing pictures, make them nice, clean, organized, labeled pictures. Use your pictures to visualize things, use your pictures to keep track of things, and we'll talk more about that in a minute. Well, maybe not a minute, maybe a day. So anyway, so vectors, first, second, third, fourth quadrant, you can choose what angles you want to use when you're doing your own calculations. But if you're trying to communicate with others, make sure that you are telling them the angle from the positive x-axis, so they know which quadrant it's in. Here they have a displacement vector that they're giving you. They're telling you what it is, d sub x and d sub y, so you can build the vector. And then you can calculate the magnitude of the vector and the angle that the vector makes. If you use these actual components in this equation down here, it will actually tell you the angle from the x-axis. So in this case, it gave an angle of negative 35.9 degrees. So that means you go to the x-axis and you go clockwise downward from the axis, negative 35.9 degrees. Wait a second, is that right?
Really with those equations, this is a diffraction angle, because there's so many different equations. I have to triple check each time to make sure that I'm doing it from the clockwise, counterclockwise angle, or from the top, from the side.
This is not right. What did they do here? Yeah, there's a lot of ways to do it for sure. But I'm trying to figure out what they did here, because they should have, this should have actually given them the correct angle, but it didn't. Did they use the correct numbers here? This is plus, this is minus. And it's giving them negative 7.25, 0.725. Maybe their calculator is just not as good as mine. I don't know. it's very possible that they're assuming that the calculator doesn't actually know. Let me think about this for a second. The tangent goes between negative infinity and positive infinity, and it skips, so it doesn't. No, this is actually true. So yeah, so there is one other caveat you have to be aware of, because, and I always forget this about the tangent. Remember the tangent function, if you remember what that looks like in trigonometry, it's this thing that goes like this and then it repeats itself, right? Over and over again. Something like that. Or I can't remember if it goes this way or the other way. But anyway, it's this repeating thing. The problem with it is that all the stuff that ends up in the negative is either in quadrant 2 or quadrant 4. So you have to decide which quadrant it is. And you decide that by looking at these numbers, obviously. So if it's a positive x, then it's in quadrant 2. If it's positive x and negative y. If it's a negative x and a positive y, then it's in quadrant 4, right? And the same thing for all the stuff that's positive. It's either in quadrant 1 or quadrant 3. If both of these numbers are positive, then it's in quadrant 1. If both of them are negative, it's in quadrant 3. And I always forget that about the tangent, but the tangent has that peculiarity because it's dividing two coordinates, right? If that makes sense to you, fine. If it doesn't make sense to you, don't worry about it too much. You will get used to doing this. The best thing to do, without a doubt, is to draw your vectors and make sure that your coordinates look correct and your components of your vectors look correct for the quadrant you're in, right? So that if you're in the second quadrant, you should have a positive x component and a negative y component. Sorry, a negative x component and a positive y component, the other way around, right? Like this one. And if you're in the third quadrant, then you should be negative on both x and y component, right? So you just got to keep track of things because you can be all over the spectrum with this stuff. So anyway. Okay, so let's do let's see here. So let's do an example here where we have a rescue party. They're wandering around on different paths. So they're going to give us a bunch of different things. They're going to go 200 meters southeast, running north 300 meters, 50 meters in direction 30 degrees west of north, directly south for 80 meters, picks up 23 degrees west of south, 50 meters, so on and so forth. All these different movements, and they show these movements somewhere here. If they should, maybe they don't. They don't, so we have to do them ourselves. Now, your first inclination is to draw a picture of this, and I would do that. You don't necessarily have to use the vectors you draw to actually do any calculations. It just helps you keep track of things. So you go ahead and draw these. And whenever you're doing homework in physics or engineering or science in general, I would recommend drawing a nice, good, clean, organized picture and putting everything that you're given on it. Because visualizing things is a huge part of understanding the math. Many people they start a physics class or a math class and they're like, these questions are easy. I don't need to draw a picture. I can do this in my head. I don't need to show my work. I can do these in my head, which is true for a little while. And then all of a sudden you start to realize you're getting everything wrong because the problems have gotten harder, but your brain hasn't gotten any bigger. Your brain has limits to it. So you got to really practice using tools that you have to visualize problems, to keep track of things, to make sure that you're understanding what's going on. I recommend to all my students that they do what I do or something similar. And it's not because I'm amazing at this. It's because I was taught this. When I was a kid, I was maybe 10 or 11 years old, and I was doing my math homework one day, nice day outside. I wanted to go and play, and I was really mad because my mom was making me do my homework. Not only that, but my window was this huge window in my room, and I could see all the sunlight. I lived on the edge of town, so I could see all the pheasants and the foxes playing out in the fields where I lived, and my dog was out running, doing fun things, and I was sitting on my butt doing math. So I was mad and I was angry. And my neighbor was kind of weird. She would just walk into our house anytime she wanted to borrow things. And she was in the house when I was yelling and screaming at my mom that I didn't want to do my homework. And she came up to my room. Yes, she was that weird. She came up to my room and she scared the death out of me, um, talking to me when I had my back turned to my door. But she came and showed me how to do homework. She was a teacher at a local Catholic school, and she showed me how to organize my homework so that I could do it faster and more efficiently and get it done better. And I've been doing it the same way ever since. Always write my name on the top. I always write what the assignment is, maybe the date or something like this. And you can do it all in one corner, or you can do it across the top, however you want. Choose how you want to do it. Just make it nice and clear what this homework is. And then start your first homework problem. Number it, problem 1 or whatever it is, so that you can come back to it easily. Then read the homework problem, figure out what it is, and represent it here somehow. Maybe you write it down. Maybe you write an explanation. Most of the time, I don't do anything like that. Most of the time, I draw a picture. So I draw a picture. I put in some vectors. I draw a picture of the person who's going to throw this. He's going to throw a house or something. So I draw a house. So he throws a house. Okay. And the house is going to go whatever else. And I want to calculate the distance that he can throw this house. So I draw that thing on there. Distance equals question mark or something like this. And then after you're done representing the problem somehow, start to write down the tools you might use, maybe equations or maybe theories or ideas. Write a list of those things down. Things you might use, tools I call them. The tools you might use, right? Write all the ones that you think you might use down, and then start looking at the problem and saying, well, from what I have and from what I need to know, which tools are going to give me the right answer. And I choose the tools that are going to give me the right answer and use them. And then I do some calculations down here. Right? Do some calculations. Maybe up here, there's things like the mass of the house is equal to 50 or something, or whatever else. Write those kinds of things down up here. And then down here, I do some calculations. When I get what I think is my answer, I put a square around it or a circle or something, or I highlight it or whatever, so I can easily find it. Now, I don't put anything over here. Why not? What's that? Space to work. I already did this. This is my space to work right here. A little space? Yeah. Why not a little space? Our brains like white space. It's actually easier to make your brain work if it's not staring at a page full of crap. And you really make your teacher angry if you ask for help and show them a page full of crap, because they're like, what am I looking at? I can't even see anything because there's so much on this page. It's really annoying. Your brain doesn't like it. Your brain likes white space. It's a place to relax. Even while you're doing the problem, you'll be more relaxed because your brain, you'll find, if you pay attention, you'll actually find your eyes just kind of wandering to that white space every once in a while to take a break. When you're not doing something, when you're not even thinking about anything, your brain, we've all done it. We all stare off into space, right? When you're just relaxing, you don't stare at the traffic. You don't stare at your 3-year-old twin brothers ripping apart a stuffed animal. When you're trying to relax, you stare into the sky, or you stare off into some blank spot in the canvas of your surroundings, because your brain wants that. Your brain wants no activity going into the eyes. The eyes have a huge amount of information coming into it. You want to cut that down to nothing and relax. And it works, it helps. How many of you have gone to sleep at night wondering about something and woke up with the answer? I have many times, especially when I'm doing physics, and you will probably experience it in this class if you've never experienced it before. One of the reasons for that is because you have no visual stimulus going into your brain at night. And so your brain has a lot more power to work on things. That's one of the reasons we dream at night, because your brain has nothing to do. It's looking for things to do. Your brain needs to do something. And so it makes up things to do. So I would dream. Right? And that's actually another way that our body and our brain relax, is to dream and just to do something that's not really anything. So white space is important. There's another reason. Why would there be another reason? What other reason might I leave this white space here? How many of you think you're going to mess up a problem in this class? Yeah, All in favor? It's unanimous. We will all screw up problems in this class, every homework assignment, guaranteed. The best thing to do is just erase, 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 and make that nasty smudge all over your paper, and then do it again and again until your paper's like see-through. That's like the best thing in the world to do, right? Wrong. First of all, it makes a mess. Second of all, it takes a lot of time. And third of all, you're out of eraser by like the third assignment. You go like through 90 pencils, you just keep adding those funny shaped erasers at the top of your pencil or whatever. And if you're using a fancy mechanical pencil, then it's really expensive by erasers. Or if you're using a pen, it's just not happening, right? I don't recommend using a pen. And certainly not an erasable pen, because those erase even worse than pencil. The best thing to do is to just put a very light cross through your work and say, wrong, or I screwed up, or whatever. And even maybe even circle what you did wrong. Maybe just say, look, this is what I did wrong. And then do it again right from the beginning, so that you do the entire process without the mistake and see how it changes things. That will change things in your brain. Your brain is, it's kind of like a lawn with moles running through it, right? You ever seen a lawn that has moles going through it? It's got all those tracks in it. Everything that you do puts a track in your brain. Every single thing that you do puts a new track in your brain, right? It doesn't matter if you did it right or wrong, it puts a track in your brain. However, if you do the same thing over and over again, and you're doing it better every time, it actually can erase wrong tracks. Your brain can actually rewrite the wrong tracks. But if you don't do it over and over again in completion, it will keep the wrong track and the right track. So you're very likely to make the same mistake again. You're much more likely to make the same mistake if you don't do it completely over again correctly. Okay. And this is not stuff I'm making up. You want to know more about that, you're going to have to take some neuroscience, but it's true. This is the way our brain works. It's kind of, it's not that simple really, but it's very similar to this. You're actually making bioelectrical connections in your brain that are semi-permanent. And you can rebuild them, but rebuilding them requires essentially the same amount of effort as building the wrong ones in the first place, right? So to rebuild right ones, you have to rebuild them right. So then you can fix your work over here and you can see that you fixed it. You can see what you did wrong. You can see how you fixed it. Learning, new brain paths are good, new synapses, and you're good, right? And I also only put one question on a page unless it's a very short question. If the question takes less than a quarter of a page or a third of a page, then I'll put two questions on it. But if it takes anything close to a half or over a half, I only put one question on the page. And I never use the backs of pages, because then you're flipping pages over all the time. That's just a pain. You're like, where was that problem? It's exactly like the one I'm doing now, except a little different. I just want to just copy what I did. And then you're like flipping things over and I have no idea what everything is. One page. Don't worry about wasting paper. Paper's a crop. Okay. It's not like we're cutting down rainforests to make paper. We cut down some trees, we pulp them, make paper, and then they plant like, we cut down one tree and we plant 3 more in its place because it's a business. It's like harvesting corn. They don't harvest trees and then not put back new ones because they know in 5 or 10 years they're going to come back and cut down the next one and sell it again. Did you know there's actually almost twice as many trees in America as there used to be 50 years ago or 60 years ago? Just because of toilet paper and writing paper and other paper. But the paper industry alone has added more trees in the United States than anything else, than more than Greenpeace or the Arbor Day Foundation or anybody else. Why? Because they make money from it. They're making billions of dollars from it every year. So that's why they do it. It's a great thing if you love trees, but it's also a great thing if you just want to do good homework. So don't worry if you don't want to buy paper, which I totally get. I keep a stack of scratch paper that's blank on one side in the back of the room here. You're welcome to draw from there if you'd like. But I highly recommend that you write your homework down on paper and you do it in a very organized fashion. You don't have to do it the way I do it. I'm not going to check it, but you're going to have a hard time convincing me you've done a good job on your homework if you bring me a chicken scratch page with 5 different problems all over it because you're just writing down calculations every once in a while when you couldn't just do it all on a calculator. You will learn better the more organized your homework looks on paper. That's just a fact. All the best scientists and engineers I've ever known have done their homework like this or similar to this. all of the scientists and engineers that I've known that have kind of ended up bombing in their careers have been very messy with their homework, all of their careers. It's just all the way, it's the way it always is. There are some exceptions, but I've never known an engineer or scientist who failed who didn't learn how to do this. Who learned how to do this, and I never knew one who succeeded who didn't learn how to do this. So anyway. Okay. So now that we're done with that, they do go through this and they do the math. Now here's the interesting thing. Now this becomes very simple to calculate the summation of many vectors. We have all these vectors that represent the different legs of this journey this guy went on, this trooper went on. And if we write down each one of these things on a paper, draw it with its angles, then we can actually build the vectors. Well, we build the vectors by using trigonometry, right? So we go back to our triangle back here. If you have a triangle that's made by this vector and its two components, one component here and one component here, this one being AX and AY, then you have a right triangle and this angle here, and you're good to go. Well, the opposite side of this triangle is the Y component, and we happen to know that the sine, right, of an angle, theta, is equal to the opposite side over the hypotenuse side. It's the ratio of those two sides. That's actually pretty much the entire theory of trigonometry, right? So then if we replace opposite over adjacent with, the opposite is actually the A component, we call that A sub Y. That's the magnitude of the Y component. And we replace the hypotenuse with the magnitude of the entire vector, which is A. Then we can actually solve for A in this equation. I said opposite over adjacent, but it's not adjacent. I always do that. It's opposite over hypotenuse. There we go. Then we can solve for A, or we can solve for A sub Y, or we can solve for theta, either way. Most of the time what we'll do is we'll solve for A sub Y by multiplying both sides by A, and we'll find out that A sub Y, or the magnitude of the component, the Y component, is equal to the magnitude of the entire vector times the sine of the angle, theta. And similarly, we find that the magnitude of the component of A sub X is equal to the magnitude of the vector A times the cosine of theta. Now, this is assuming, of course, that this angle that we know is opposite the Y component side of this triangle. If we don't know this angle, but we know this angle up here, well, this angle is opposite the X component. So that would change. This would become the sine, and this one would become the cosine. But if you know this angle and you know that we have a right angle here, you can always find this angle. So you can always use the other version as well. So you can always use this version if you use the right angle, correct angle. So they do that for each one of those legs of the trip in that example. And so they get components for each one of those legs of the trip. And after they've got all the components of the legs of the trip, then they can just add up all the X components from each leg, add up all the Y components from each leg. Let's see, I gotta go all the way down again. And then we get the total components of all those vectors added together. So here they've got the first leg of the trip, and then the second, and then the third, and the fourth, and the fifth. Once they've got all those together, then they can add them all together and get the total overall X component and total overall Y. All right, so that takes us to the section on polar coordinates, which we will have to save for next time. Before we leave, before you guys leave, I have some, let's see, do I have enough lab kits yet? I'm not sure. But before you guys leave, we'll try to get you your lab kits. Did you guys out there in Zoom land get your lab kits yet?
I haven't gotten mine yet. I just saw the message that you had.
Sorry.
I just saw the message that you had sent them to the college here in
Okay.
town.
Did anybody
so
else get their lab kits?
I have not.
You have not, okay. Maybe email me when you do get the lab kits so that I know they got there. And then we can also make sure that we have the right due date. We don't want the due date for the first lab to happen before you get your lab kits. For those of you, and thank you, well, before you leave, actually, I have one more question for everybody. What would, I've been toying with the idea of changing this class next year to a Tuesday, Thursday class that meets for 1.5 hours-ish instead of a Monday, Wednesday, Friday class that meets for 50 minutes. What do you think about something like that? Would you prefer to spend more time, fewer days, or more days, less time? You like fewer days meeting and more time each class? Because that's what I prefer as well. And I found that most of my students do better the longer we spend on a subject in one go, rather than smaller times, more days. But
Yeah, fewer days, more time.
So Matt, you like the more time idea?
No, I'm lying.
So you like more time, fewer days, or fewer, or more days, fewer time, less time?
Fewer days, more time.
Okay, you
Is
like
what I
that?
prefer.
You guys have anything in here? Okay. Yep. Yeah, true. Anybody else have any thoughts? Taylor or Lane?
I'm fine with either, but I think I would learn best that way as well, with
Okay.
less days, more time.
Okay. And I always forget your name. Why do I always forget your name? Dustin. Dustin. Yeah. And I think that's really the case with most students. Most students tend to put their homework off anyway. And so the fewer days we're meeting, the format usually goes, when I have fewer days, it usually goes, we'll spend the first day, we'll just burn through the chapter as quickly as we can and get as much done as possible. And then the second day will be finish up whatever we didn't quite finish and then just review homework problem questions. So any problems, any questions you have for homework, so that to that point, we answer questions for like over an hour. And then students tend to actually get most of their homework done by the end of the second class, so that they just have to go home and kind of mop up a few things and maybe do a problem or two and be done. But that's just my thought. I mean, if any of you, if all of you wanted to switch to that kind of format next semester, we could do it, but everybody would have to want to do it. We would not change for just if even one person didn't want to change it. But next year I think I might change it. So I just wanted to know your opinions. Thank you very much. We will see you guys on Friday to finish up the chapter and also to answer any homework questions. So get started on homework. You should be able to do a fair amount of it at this point. We're only 2 sections in, but the rest of the sections are mostly just things that we've already been talking about. So except for the
I just wanted to tell you real quick.
Yep.
It says that the second experiment is due tonight.
Yeah, I'll change all those due dates for experiments and when we actually get the lab kits in your hand. So don't worry about experiment due dates. I'll change them all and we'll adjust that for when we get the lab kits. All right, thanks.
Okay. Yep.
Thank you.
Have a good day.
You too.